In this lecture, we're going to discuss inverse trig functions. Now, the 6 trig functions that we are aware of, sine, cosine, tangent, cotangent, secant, and cosecant, none of these are one-to-one over their natural domain. Therefore, as a consequence, they don't have an inverse by definition. So, we still like to be able to use these functions in order to be able to establish a two-way communication between the input and the output. So, as a result, what we need to do is we need to restrict the domain, the natural domain that is, of these functions, so we can find the inverses. Now, the restriction on these domains may not be unique, although there are some common convention that softwares, calculators, and textbooks have agreed upon, but there are some variation still in restricting the domains, more specifically for secant and cosecant. But the restricted domain for sine, cosine, tangent, and cotangent, those are pretty universal. But again, you will see variation, at least in calculus textbooks, on how they restrict secant and cosecant. Now, here is how the sine, first I'm looking at the first part, I'm looking at the sine function. Remember, the sine continues, of course, like that. So we're only looking at a portion of it which passes the horizontal line test. In other words, makes the function one-to-one. Same thing with cosine. Over the domain from 0 to pi, cosine becomes a one-to-one function. So likewise, these other 4 functions. Therefore, they will possess an inverse now. So if these are the functions, then to the right you'll see their inverses. Okay, so if I focus on, for instance, the sine function, this would be the inverse of sine. Remember, one attribute of a function and its inverse was that the role of range and domain are swapped out. So in here, let's say in the case of a function, if I have an xy, then with the inverse, same point xy turns into yx on the graph of the inverse. So for instance, let's take a look at this point. This point is pi over 2 and 1. Right? So if I look at the graph of the inverse now, on the graph of the inverse, that point is 1 comma pi over 2. You see that? So that still holds, where you switch and swap out the coordinates of x and y in order to get the inverse. So you can see the restricted again domain for each of these graphs, and our focus is on the inverses. So for sine inverse, the restricted domain is from -1 to 1, right? -1 to 1. Okay, and for cosine, it's going to be -1 to 1 also. And for tangent, it's from -infinity to infinity, right? And so on and so forth. Now, our focus will primarily be on sine, cosine, and tangent inverse. We could get the others, cosecant, secant, and cotangent, using reciprocal identities. We can actually do that. And I'll show you how to do that maybe as I do the exercises. But one thing that's important to note here is that not only the domain of the inverse, but the range of the inverse is important. So the range of sine inverse is from -pi over 2 to pi over 2. The range of cosine is from 0 to pi, and so on and so forth. One way I have this thing down that really helps me is the following. If I draw the circles, let's say these could be the unit circles. So when it comes to, let's say, sine inverse, for sine inverse of x, the range, not the domain, but the range of sine is from -pi over 2 to pi over 2. Okay, that's the range of sine. For cosine, the range is going to be from 0 to pi. Okay, so this is something that helps me remember these ranges. I actually use a circle. Now, if I actually use a half circle, that makes it a little easier. There you go. So those are the ranges of those inverses. Now for tangent inverse of x, tan is ratio of sine to cosine. So places where cosine is 0, right, the tangent doesn't exist. Therefore, that would be at 0 and pi, right? Places where cosine is 0. Actually, sorry, that would be at pi over 2 and negative pi over 2 for cosine to be 0. So the range of tan inverse is just like sine in that it goes from 0, from negative pi over 2 to pi over 2. Okay, that's where it goes. And now notice I have open circle at those because at those points cosine is 0. Now if I want to find the range of cotan inverse, you see how quickly I can get these from the circle. For cotan, I use the same drawing as I did for cosine, because cotan is ratio of cosine to sine. And there you go. This time, places where sine is 0, I have open circle at 0 and pi. So this is the range of cotan inverse. Now for secant inverse, secant is ratio of 1 over cosine, right? So it's going to be exactly the same as cosine inverse, right? And of course, it cannot be pi over 2 because cosine of pi over 2 is 0, right? So for secant, it's going to go from 0 to pi over 2 and then pi over 2 to pi. That's the range of inverse. But you will see up here, let's take a look at secant. For secant, there you go. The range is from 0 to pi over 2, excludes pi over 2, and goes from pi over 2 to pi. Now other textbooks may, for instance, restrict it differently, but this is the common sense way, the way this book is doing it. And common sense, and I'm talking in the sense that secant is the ratio of 1 over cosine. So look at my circle, looks the same as that of cosine, except I need to make these. There you go, 0 and pi. Those should be included. So it looks just like my cosine inverse, with the exception of division by 0 at pi over 2. Now, the range of cosecant inverse of x, because cosecant is ratio of 1 over sine, so I'm going to duplicate the graph that I have for sine. There you go. So make it work for sine, which is negative pi over 2 to pi over 2. And of course, cosecant of 0 is undefined, because sine is 0 at that point. Okay, and there you have it. And that's exactly what it is for cosecant right over here. Okay, this is again something that personally I use. I highly recommend. Remember, it's much easier to remember the circles, or the half circles in this case, and being able to produce those ranges, because we will need these ranges later on throughout the calculus series as we work with the inverse functions. Okay, next, let's take a look at the definition of inverse trig functions here. We have y equals sine inverse x if and only if x is equal sine y. So that's the definition of inverse. Okay. The inverse function cosine x, y is inverse cosine if and only if x is equal to cosine y. Okay. And so on and so forth. Now notice we have the domains of these. The domains are the same as the restricted domain of the respective function. Like for sine, cosine, the domain of the inverse, these are the inverse functions, would be the same as the ranges of respective trig functions that they came from. So in the case of sine cosine, remember the range of sine and cosine lie between -1 and 1. So in that case, the domain of inverse becomes -1 to 1, and likewise for the rest of them. Now, as we go forward, by the way, in future sections, and well, we are nearly done with this chapter, so you won't see us using this, but in, let's say, second and third semester calculus and beyond, the most commonly used inverse trig functions would be sine, cosine, and tangent. And the others we can actually create if we need to. Now, one thing that's important here I want to point out as we go through this, that the output of every trig inverse, that is, inverse trig function, their output is going to be the measure of an angle. So, for example, to give you an idea what I mean, well, we know sine of, for example, pi over 6 is 1/2. That's just the sine function, right? So a point on the graph of this function is pi over 6 and 1/2, right? Now, if I swap the points, if I swap them, then I get 1/2 comma pi over 6. This will be a point, so I'm just going to this is a point on the graph of f of x, right? And my f of x is the sine function. Okay. Now, if we switch this, then this becomes a point on the graph of the inverse function, right? Of f inverse x. That's what that becomes. Now, so what that means is that if we use the sine inverse, just like we use the notation f, we use f inverse x. So for sine, we use the inverse notation. Sine inverse at 1/2 is equal to pi over 6. And there you go. So this is what I mean. The output of every inverse trig function is an angle. Okay, this is what the output is, pi over 6. So please keep that in mind. Now, let's take a look at the inverse property of trig functions. We know that for all functions and their inverses, the composition of the function and its inverse gives you the identity function x. True? So, same holds with these functions. They're no different. That holds what we said, the composition equal x holds for all one-to-one functions and their inverses. Now, when it comes to trig function, the composition of sine inverse is x, and the composition of sine inverse sine x is x. See that? Composition in both directions. And there you go. This is true for the other three trig functions. So secant inverse x is x, secant inverse secant x is x, and so on. Now, one thing that's very important is that this is true provided we are in the domain of the inside function, the inverse, the domain of the inverse function. Or you can say this is true if we are in the range of the outside function. You see that? The domain of inside or the range of the outside function. So in the case of, let's say, right in here, this identity holds tan inverse of tan x equal x, provided that x is negative pi over 2 to pi over 2. That's in domain of inside function. Or the same thing, that would be, this is the range of inverse, right? The range of inverse, tan inverse, is from negative pi over 2 to pi over 2. So domain of the inside, range of the outside. So if I look at this, for instance, this holds if we are in the range of cosine, which is from -1 to 1. See that? So that's another way to state these properties. And it's important because in a moment we'll see exercises where you have to do things like this. So the composition isn't always going to be just x. Keep that in mind. You got to pay attention to what is the given range of the outside or the domain of the inside function. Okay, in the case of the function inside, if it's just sine, cosine, and so on, you look at the domain. With respect to the outside inverse function, we look at the range. Okay, and here you have a note here that these properties hold only for specified values of x. This is what they mean, those specified values of x. If they're not, we need to work it somehow, that we use the idea of maybe coterminal angles or angles that have the same trig measures to bring it into the range of the inverse. Okay. Now, next what we have here is we have the derivatives and we have the integral of inverse trig functions. The proof of these, by the way, are in the book. I'm not going to prove it because it's just going to make the video too long. There's too many of these. The derivative of sine inverse is 1 over square root of 1 minus u squared. Cosine inverse is what you see, and so is tan. Typically, in an in-class situation, we expect the students to have memorized the first 3. Because otherwise it's too much memorization. These we don't use as often, although that's what they are. But the first 3, typically students need to have those memorized because those will occur more frequently in future chapters of calculus and calculus series. When it comes to the integral of those, well, if the derivative of arc sine is that, it makes sense that the antiderivative of this will give you back the arc sine. And that's what these are, to the right. To the right are antiderivatives. And that is it. So with that, let's actually take a look at some exercises here. Alright, so let's take a look at these exercises for now. And we're going to look at numbers 1 through 24. Okay, so let me bring up this one also, and maybe right there, and we're going to work some of these out. Let's begin with exercise number 2. Okay, in exercise number 2, the question says find the exact value of the given expression. Now remember what I said earlier. The output of every inverse trig function is an angle. So call that angle theta. In numbers 1 through 6, I want to know what theta is. 7 through 12, same thing. We want to know what theta is, the measure of an angle. And then right up to 16, that's what we want to do. And then beyond 16, we're looking at a composition of inverse trig function and just a trig function. So that's going to be different. But the first 16 problems, we want to find theta. So let's begin with number 2. In number 2, so I'm going to call theta. See, that's what I meant. Rather than writing it the way they have it, I'm going to write that as theta equals to that. Now, by definition of the inverse, I can write sine theta is equal to, this is cosine, so I can write cosine of theta is equal to 0. Now, here's where the domain, restricted domain, comes in, or the range of the inverse for cosine, and I'm going to do this so it becomes second nature for all of you. Okay, so I'm looking at cosine inverse. When I work with cosine inverse, I look at the restricted domain of cosine. Remember, cosine is from 0 to pi. This is the range of the inverse or restricted domain of cosine. Okay, so we're looking at cosine inverse of x here. So cosine of what angle is 0 in 0 to pi? clearly cosine of 90 degrees is 0, right? So the measure of angle theta in this case is pi over 2. Okay. Now note, by the way, we know if I look at the full circle over here at 3 pi over 2, right? 3 pi over 2, cosine of that is also 0, right? But we're not going to count it because that's not in the range of the inverse, right? So for that reason, it's important to note what these ranges and domains are. Okay, so there you go. That's the answer to number 2. Now if I look at, for example, number 6. In number 6, I have, again, I'm going to write theta is equal to tan inverse of -1, or arc tan. So, by the way, the inverse is also called arc. So tan inverse is also, some books write it as arc tan of -1. Okay. So for this one, let's bring up our circle for tangent. Remember, for tangent it goes like this. Here's negative pi over 2 to pi over 2. Right? That's going to be the range of inverse for tan inverse. So by definition of inverse, tan inverse of an angle theta must be -1. Now, a lot of these exercises, in fact most of them, are going to have special angles for which we know the exact value for the trig functions of that angle. So here we need to think about, okay, tangent of what angle is -1, right? Now we know tangent of, for instance, let me go back to my circle. Tangent is negative when ratio of sine to cosine is negative. So tangent is negative here, right? It's negative here, and it's negative in the second and fourth quadrant. The measure of the angle here would be, let's see, that would be pi over 4, 3 pi over 4, and 4, 5, 7 pi over 4. Right? So that's where tangent is -1. But note, if you note, neither of these is within the range of the inverse. You see that? We have to be either in the first or the fourth quadrant. The answer should be in here or in here, first or fourth quadrant. Now, so what we need to do, we're going to rule out 3 pi over 4. We're going to stay with 7 pi over 4. Now that we can actually, even that 7 pi over 4 is not in the -90 degrees to let's say 90 degree range. So what are we going to do with that? Well, in this case, we're going to go in a clockwise direction and create an angle that is coterminal to that. The coterminal angle is going to be negative pi over 4, right? And that puts us right inside of that fourth quadrant within the range of the inverse. Therefore, from this we get theta is going to equal negative pi over 4. You see that? So you just have to make these adjustments to find these exact values. Now we're not doing any calculus, by the way. This is all just a review of your trigonometry so far. In number 10, we have cosine inverse of -1 over root 2. Okay, number 10. We have, let me write theta equal cosine inverse -1 over root 2. So from this, again, by definition of inverse, we have cosine of theta is -1 over root 2. So the measure of the angle is going to be 45 degrees, right? Cosine is negative. So ordinarily, with respect to unit circle, cosine is negative in the second or third quadrant, right? So the reference angle is pi over 4. The angle itself is going to be, again, 3 pi over 4 or 5 pi over 4. Now, neither of those are within the range. Well, actually, yeah, one of them is. this one. That one is within the range of the inverse, which goes from 0 to pi. You see that? 0 to pi. So the only measure of angle that's acceptable in this case is 3 pi over 4. So the answer to theta is 3 pi over 4. Okay. Let's do something different. These are all sine, cosine, tan. Okay, let's take a look at something in the way of cotangent, secant, and cosecant, maybe some of those. Let's take a look at number 14, for example, where we have cosecant inverse. Number 14, theta is cosecant inverse of number 14 of root 2. Again, by definition of inverse, that means cosecant of theta is root 2. Now, for cosecant, let me draw my circle. Cosecant is 1 over sine. So check this out. I'm going to draw my half circle. Okay, this is the range of inverse cosecant. It's going to be the same as, because cosecant is 1 over sine, right? So I'm going to actually recall what sine, the range of sine inverse was, which was from 0 to pi, and the exception because of division by 0 here at pi over 2, we're going to exclude, and that's not going to be in the range of the inverse. Okay, so there you go. That's the range for cosecant inverse. Okay, now the measure of the angle itself. Let's see, if cosecant theta is root 2, that means sine theta must be 1 over root 2, right? Because cosecant is 1 over sine. Now at this point, I'm going to search for which special angle has sine 1 over root 2. And that's going to be, again, a 45-degree angle. So sine is positive here at 45 degrees, and sine is positive in the first and in the second quadrant, right? Now, let's see. So pi over 4 and... hold on. I'm doing sine, right? I didn't do my circle, right? My apologies, sorry about that. But this is true. What I was about to write is right. There you go. Sine of pi over 4, 3 pi over 4, both of those are permissible for sine to be 1 over root 2. Now, my circle, though, looks like this. Remember the circle for sine inverse? It looked like that. And actually, for cosecant inverse, it isn't allowed to be 0. Theta cannot be 0. The 0 of sine, right? Division by 0 here. So that looks right now. Okay. Therefore, we're going to only accept pi over 4. We're not going to accept 3 pi over 4. Therefore, the answer to this exercise is pi over 4. Okay, for number 14. Let's take a look at, let's see, I've done tan. Let's take a look at something. Notice most of these are sine, cosine, and tangent inverse. Let's take a look at number 20. Number 20, we have cosine of 2 sine inverse 1/2. That's number 20. Now this is not the measure of an angle, right? Because I have cosine, and the argument of the cosine, the angle of cosine, notice is 2 sine inverse 1/2. And this is what I meant. See, that's going to be theta. So this is like a cosine of 2 theta in that form. So I need to actually, if I let theta be sine inverse of 1/2, or again some call it the arc sine of 1/2, if I let it be that, then by definition of inverse, sine theta has to be 1/2. And again, sine is a half. If you think about your unit circle, sine is 1/2 for pi over 6 and 5 pi over 6, right? But the range of inverse goes from negative pi over 2 to pi over 2, just like it did up here, right? So it's going to go from negative pi over 2 to pi over 2. In other words, between negative 90 and 90 degrees. So the only acceptable measure is going to be pi over 6. And now this becomes just cosine of 2 times pi over 6, which is cosine of pi over 3. And cosine of pi over 3 is cosine of 60 degrees. That's a special angle, 1/2. Okay, so there's number 20. Let's take a look at another one, maybe 24. In 24, we have secant of arc tan of 2. Number 24. We have secant of tan inverse of 2. So remember, this is our theta. Inside is theta. So that means by definition of inverse, tan theta is 2. So now this is not a special angle. We need to actually draw a triangle here and find measure of the find secant from the triangle. So let me call this theta. Now remember the range of tangent. Let's have that on the side. Tangent is the same as sine inverse. I'm looking at the range of tan inverse, not tangent. So it's going to go from negative pi over 2 to pi over 2, just like sine does, except the endpoints are not included, because at the endpoints cosine is 0 and tangent, being ratio of sine to cosine, is undefined. Okay, so tangent is 2. Now I'm going to write this 2 as 2 over 1. Any number, you can write it as itself over 1 without changing the number. Now, 2 over 1, if you go back to definition of tangent using the triangle definition, remember tangent is the ratio of opposite to adjacent, right? So when I label my triangle here, I'm going to label this side 2 and this side 1. Okay, now if I do that, then the hypotenuse of this triangle by Pythagorean theorem is going to be square root of 5, right? That's 2 squared plus 1 squared makes 5, square root of that, according to Pythagorean theorem. So we have constructed our triangle. Now from triangle, this is like finding secant of theta. And here's my theta. You see that? So from the triangle, I'm looking at the triangle, I'm using secant as 1 over cosine theta. So that means 1 over adjacent to hypotenuse. So secant, ratio of hypotenuse to adjacent. You can also do it that way. And however you look at it, the answer to this is going to be hypotenuse is root 5, adjacent is 1. So the answer is root 5. Equals root 5. That's the answer. Okay, and there we have it. So if something is not of a special angle, we need to draw the triangle and get it from the triangle. That was number 24. Now let's see, let me bring more of the exercises and we'll do more of these. There you have it. In this next segment of the exercises, the question reads, write expression in algebraic form. So let's begin with number maybe 28, and then we'll look at 32 because it's got cosecant, cotan, something we haven't worked with. Now in number 28, we want to find tangent of arc sine of x, sine inverse of x. We want to write it as an algebraic expression, what this is. So let's begin with looking at this as tangent of theta, where theta is inverse sine x. So by definition of inverse, then that means sine theta equal x, right? Now, this x, I'm going to write it as x over 1, just like I did in this example. I'm going to think about definition of sine. Okay, definition of sine, which is sine is the ratio of, in a triangle, is the ratio of opposite to hypotenuse, isn't it? So I'm going to draw my triangle like this. Here's theta. Opposite is x, hypotenuse is 1. That's how I get this ratio. Okay, now from Pythagorean, this side has to be square root of 1 squared minus x squared, which is root 1 minus x squared. Right? That's from Pythagorean theorem. And at this point, when you establish your triangle, then I can find tangent of theta directly from the triangle. Okay, tangent, ratio of opposite to adjacent, 1 minus x squared. And there you have it. That's what that is. You don't need to rationalize the denominator in this segment. It's very important to draw the triangle, otherwise you cannot do this. Let me do number 32. In number 32, we have cosecant of Cotan inverse of x. Okay, so again, we see this as cosecant of theta, where theta is Cotan inverse of x. And by definition of inverse, cotangent of theta is going to be x. Write it as x over 1, and go to definition of cotangent. Now, cotan is 1 over tan. So for tangent, it was opposite to adjacent, right? For tangent, opposite to adjacent. So cotangent is going to be the ratio of adjacent to opposite in a triangle. I need that in order to construct my triangle and label it appropriately. Now, adjacent is x, hypotenuse is 1. By Pythagorean, the opposite side would be square of the hypotenuse minus the square of the other side, square root of it. And there you have this one. And from this, now we can get cosecant of theta. And remember, cosecant, again, is the ratio of 1 over sine. Sine is opposite to hypotenuse. Reciprocal of sine makes it hypotenuse to opposite side on the triangle. So it's going to be 1 over opposite is 1 minus x squared. See how that works? And there you go. That's let's see, that should be that. Maybe make sure I got this right. So again, cotangent of theta was let me make sure this is right. I see. Actually, let me backtrack. I did say this right. I didn't set up my triangle right. Adjacent is 1, and I said opposite is adjacent is x. Opposite is 1. Opposite is 1 means this side. Sorry. So the hypotenuse is actually 1 plus x squared. Glad I caught that. Okay. No problem. We just adjust this part. Now, cosecant, the ratio of hypotenuse to opposite, is going to be square root of 1 plus x squared over 1, which is root 1 plus x squared. There. So you just got to make sure you label the triangle as I didn't correctly, and that should be fine. Let's take a look at more of these. Let me bring this one up. Okay, so now in this segment we're going to take a look at the ones I have circled here. Now, because in this segment we are doing derivatives of these functions, I went ahead and copied those derivative formulas for you in here for reference. Okay, so I'm just going to follow the formula for each of these. In number 34, g of x is cosine inverse of 2x minus 1. Okay, so g prime x, the derivative, we're working with cosine inverse, right? So it's going to be negative. Make sure you catch that negative. I wish it was a space another pixel away from the fraction line. So we have negative of 1 over, in this case, u is 2x minus 1, right? So it's going to be square root of 1 minus parentheses 2x minus 1 quantity squared. And then chain rule, right? Times derivative of the inside function times 2. So that's what number 34 turns out to be. And let's see. Pretty much that's, let me see if we can simplify this one. Next, I'm going to try to simplify this. Should be able to simplify the bit. So this is going to be negative 2, right? Here's negative, and there's the 2. Put those in the numerator. Now, in the denominator, let me do that separately. When I square the radicand, the binomial in the radicand, this becomes negative of 4x squared, negative 4x plus 1. And then distribute, we get 4x minus 4x squared. The 1 and negative 1 add to 0. And then, let's see, I can factor a 4, so it's going to be x minus x squared, right? That's what I'm going to write. That's going to be square root of 4 times x minus x squared. Now, square root of 4 is a 2, so that's negative 2 over 2 times the radical, x minus x squared. The 2's cross out, so the answer is going to be negative 1 over square root of x minus x squared. And there you have that one. Okay, that's number 34. That was 34. Let's take a look at number 40 now. In exercise number 40, g of theta is secant inverse of theta divided by theta. Now for this one, number 40, we're going to do the quotient rule, right? So let's call it g prime theta. G prime theta is going to be, that's going to be theta squared. Repeat the denominator times derivative of secant inverse. Derivative of secant inverse is going to be this. It's almost like sine. You see that? Actually, sorry, u squared minus 1. Sorry, look at the one above it. But they're swapped out. Sine and cosine is 1 minus u squared. Secant, cosecant is u squared minus 1. And then there's this absolute value of u that's in the denominator. Now again, the negative on, look at the negative on all the co-functions. All the co-functions, the derivative is negative in front of it. So I'm just going to use this formula for secant. It's going to be 1 over absolute value of u squared of u squared minus 1. And that's going to make this let me see, secant inverse. Okay, 1 over, we're doing the derivative of secant, so it's going to be 1 over absolute value of theta square root of theta squared minus 1. Right, I just did what's in the formula. And then du dx, u is theta, so the du d theta, actually not dx, du d theta in this case would be 1. Okay, and let's see, so that was first time derivative of second minus the numerator times derivative of the denominator, which is 1. Okay, and that's what that turns out to be. So let's tidy up this thing. We do have theta. We can multiply top bottom here, or actually maybe I can separate it. Hold on, let me see. Okay, here's what I can do. I can actually, because I'm dividing by theta squared, the monomial, I'm going to divide each term in the numerator by the denominator. So when I do that, in other words, I'm looking at that by itself. Notice in here I can divide the thetas out, right? When I look at it as a single fraction. So it's going to be, first part is going to be 1 over theta, right, times the absolute value of theta, square root of theta squared minus 1, negative, now I'm doing this part, secant inverse, theta divided by theta squared. And we're going to leave it like that. Doesn't simplify well at all. There's number 40. Let's take a look at 44. Number 44, we have secant inverse plus cosecant inverse. So y is equal to secant inverse x plus cosecant inverse x. Now, we just did the secant inverse, right? So it's going to be using our formula. It's going to be y prime is 1 over absolute value of x, square root of x squared minus 1. That's using our formula. And then we have a similar formula for cosecant inverse. Let me show you. The one directly above it, they look the same almost, right? The difference is in minus here. So I'm just going to write it negative. The same thing. Oh, interesting. These are opposites, aren't they? 0. So the derivative of that would be 0 at every point. Now, interesting. Let's see if I can graph this function just to kind of see what it looks like. It looks like, remember, y prime equals 0 means the slope of a tangent is horizontal always. I went ahead and graphed, actually, in using Desmos. I was curious. I graphed this function. You can see the graph is to the right. Secant inverse x plus cosecant inverse x. And the graph, you can see it's a flat line, horizontal line. That's why the slope of a tangent is 0 at every point. Now, the reason there is no, notice there is a gap in here between like -1 and 1, right? The reason that has to do with the domain of secant and cosecant, right? Because domain of both of those turn out to be from -infinity to -1 union 1 to infinity. It's for that reason. There's nothing in here. So that's interesting. I was just curious, and that's what it turned out to be. Okay, so that's number 44 for us. In number 50, let's take a look at that one. So we want to do arc tan of cosine theta over 2. Number 50, h of theta is going to be arc tan of cosine theta over 2. Again, notice I mentioned arc tan. A lot of textbooks, even the softwares, if you try to input a function into like Desmos, Desmos would not understand the inverse notation, because if you do, it will mistake it by 1 over whatever, the negative exponent. So if you want to graph this, let's say in a graphing utility or software, you may have to call it arc tan of x. So the software syntax would accept that. Okay, now the derivative of this one, so we're going to work with arc tan. Okay, now arc tan is easy to remember also, is 1 over 1 plus u squared. For cotangent, it's going to be negative of that. Okay, so this is going to be like u, and then h prime theta is going to be, so it's going to be 1 over 1 plus u squared, that's cosine theta over 2 quantity squared, times du is the derivative of 1/2 cosine theta, which is going to be half derivative of cosine is negative sine theta. Okay. And so I'm going to put the negative in front of the fraction. The sine theta, let's see, 1/2 sine theta. In the denominator, I have 1 plus cosine squared theta fourth. And I can multiply top bottom of this by 2. Or actually, let's multiply by 4 to get rid of the denominator. So this becomes negative 2 sine theta. That's 4 times 1/2 in the numerator, 4 times 1 in the denominator, plus cosine squared theta. That's looks good. And there you go, number 50. That wasn't bad. From number 50, we go to number 56. In number 56, we have the function is half of tan inverse x plus 1/2 natural log. Boy. Okay, let's take a look at this one, number 56. Now I can go ahead and distribute the 1/2 inside. Okay. Or we can keep it on the outside, it doesn't matter. So first, let me write number 56. In number 56, f of x is 1/2 of arc tan x plus 1/2 of the natural log of x plus 1 over x minus 1. Okay, make sure I copied it right again. Arc tan half natural log. Yeah, looks good. Okay, so for this one, we're going to do the f prime x. We're going to use the sum of derivatives, right? Derivative of arc tan is 1 plus x squared plus 1/2. Derivative of natural log is 1 over the argument, ln of u, 1 over u, which makes it x minus 1 over x plus 1, right, times chain rule, the derivative of the quotient inside x plus 1 over x minus 1, that derivative. Now, be easier, actually, let's not do that. That ln of x plus 1 over x minus 1. Let's rewrite using properties of logarithms as ln of x plus 1 minus ln of x minus 1. There. Let's do that so I don't have to do quotient rule. Okay, so that's 1/2 times derivative of ln of x plus 1, that's just 1 over x plus 1 minus 1 over x minus 1. See how much easier that became? And there you have it. Okay, let's see, what else can we do? So I'm gonna work this fraction. Now that segment, we're gonna work the difference actually. Now let me combine 1 over x plus 1 minus 1 over x minus 1. The LCD, of course, is x squared minus 1, which is their product, right? Difference of two squares. So I need to multiply the first fraction by x minus 1 to build it to the LCD, the second fraction by x plus 1. And that combines into negative 2 over x squared minus 1. Now, negative 2 over x squared minus 1, I can write it as 2 divided by 1 minus x squared, right? Bring the negative in front and distribute it in front of the denominator and distribute it. So this becomes 1/2 1 over 1 plus x squared plus 1/2 times 1 over 1 minus x squared. Okay. Now, at this point, what can we do? We can, maybe I can bring out, let me see, the 1/2, right? Let me see if I factor the 1/2, what's going to happen? Actually, oh, okay, I see what happened. The 2 that's in the numerator, I left that 2 out. Okay, so here's a 2 in the numerator. Now I can actually cross out the 2's. That worked out nicely. Perfect. So this is going to become 1/2 of, and the LCD now is 1 minus x to the 4th. So the first fraction here, let me show the steps in this one. X squared plus 1 over 1 minus x squared. Okay, in this one, do multiply top to bottom by 1 minus x squared, because the LCD is 1 minus x4, that's why. Plus 1 plus x squared, multiply top bottom of the second fraction by 1 minus x squared. Now I have a common denominator, right? And that's the product of the form a plus b times a minus b, difference of 2 squares. That's how I get 1 minus x to the 4th. Okay. In the numerator, I have 1 plus 1 is 2, and the x squares cancel. Interesting. So this is just 2 divided by that, and the half in front cross out. So that works out really well. 1 over 1 minus x to the 4th. That's the answer to to that exercise, number 56. Again, the key was to recognize here, which saved me probably a few steps, right, in avoiding doing the quotient rule for the derivative of the inside of natural log. And okay, so we're good with this segment. That brings us to some integration problems. Okay, so let me grab our formulas for the integration problem. Okay, so I moved the formulas here for our integration problems down here. And we're going to look at the circled exercises. Let's begin with exercise number 68. Here we want to evaluate the integral. So in exercise number 68, we have the integral from 0 to 4 root 3 of 1 over x squared plus 16 dx. Now, when we look at these integrands for this segment, for all of the ones in this segment, we need to match the given integrand to any one of the ones that you see above here. So, looking at number 68, let me clean up this mess. Okay, so for example, I can immediately rule out a possibility of a secant inverse somehow for the answer. True? Because look at that, the radicand, what's important is the radicand, and of course on the outside too. But more importantly is what's in there under the radical sign, the radicand. Is u squared minus 1. This is not like it. I don't have a square root at all, in fact, right? Out, 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 ruled out. Because all of those involve square roots, and I don't have that. So my only possibilities are either what you call it, Cotan or tan inverse. Okay, now because the integrand is positive, not negative, so we're just going to try the arc tan. Okay, so now when we focus on one that we think is the right candidate, now look at the structure of the right side and look at the one we have. That's not quite the same, is it? What's important here is the 1, right? Look at that. I don't have a 1, I have 16. So I need to work it to where that's going to become a 1. It doesn't matter what this is, which means here. At this point, it doesn't. First and foremost, what's important is to have that 1 in that position. So, to that extent, I'm going to actually factor a 16 from the denominator. Okay, so factoring a 16 from a denominator becomes 1 plus x squared over 16. You see that? It's getting closer to what this form should be. Now I can see here clearly that my u squared is x squared 16, so I'm going to let u be x over 4, right? The square root of that. And with that, we're going to proceed. du is going to be 1/4 of dx, right? And so from this, 4 du equal dx. Perfect. Now, I'm going to work my indefinite integral of, so we're going to work 1 over 1 plus x squared over 16 dx as an indefinite integral. Means I don't worry about the limits of integration at this point. Okay. And this is going to become, using our substitution, so it's going to be 4, and actually hold on just a moment. Okay, so it's going to be 4, let's say it's 4 du, so it's going to be 4 times the integral of 1 du. Okay, that's my dx. 1 plus, and then that's u squared. There you go. So that's pretty easy to do. And that integral is going to be 4 and then arc tan of u plus a constant, right? That's what that is. Now I can actually do my integral. Therefore, the integral of 0 to 4 root 3 of 1 over x squared plus 16 dx becomes 4/16. Remember, we brought 1/16 on the outside. It's going to be 4/16 times arc tan of u, which is x over 4, evaluated from 0 to 4 root 3. There you have it. Now, I do need to evaluate this, right? So let's evaluate the integral. The integral becomes, here's 1/4, that's 4/16, right? Becomes 1/4. The fundamental theorem kicks in. That's going to be arc tan of 4 root 3 divided by 4 minus arc tan of 0 divided by 4. Okay, and this is going to be now 1/4 arc tan of root 3 minus arc tan of 0. Okay, now we need to evaluate this actually. So we're done with the calculus. Let's do the trig part, of it. If I call these angles, remember the output of every inverse trig function is an angle. So if I call those angles alpha and beta, then I can write alpha is arc tan of root 3, which means tangent of alpha is root 3. Now tan alpha root 3, I need to draw a triangle. This is going to be a special angle. 1, 2, 3. This is 60 degrees. Tangent, opposite to adjacent, so the reference angle is pi over 3 or 60 degrees. Now, with this, we're also going to consider the range of the inverse, right? That's why these half circles I've drawn earlier become meaningful. So here's your alpha. Okay, and this goes from negative pi over 2 to pi over 2. Okay, now let's see, from the triangle we know that tangent of 60 degrees is the square root of 3. So that's going to be pi over 3, also 4 pi over 3. Right, and those both have tangent, which is the square root of 3. However, if you look at the range of the inverse tangent, we're going to rule out 4 pi over 3 because it's not in this range, right? Our range is right in here. It's got to be from negative pi over 2 to pi over 2. Anything outside of that, we're going to rule out. So we're only going to accept pi over 3 in this case. And therefore, alpha is going to be pi over 3. Now, for beta, we know tangent of beta is 0. And again, by the same token, the only way tangent can be 0 inside the range of the inverse is if beta is 0. and that takes care of what's inside the bracket. So it's going to be 1/4 simply pi over 3 minus 0, which the final answer is pi over 12. And there we have the answer to that integration problem. So very interesting. That's number 68 for us. Okay, hopefully you can follow the work that just took place. I really highly recommend drawing these half circles that I've drawn earlier in the lecture. Otherwise, it's gonna get confusing. How do we know whether to, in this case, go with pi over 3 or 4 pi over 3 when there's multiple choices for the measure of the angle? All right, let's take a look at number 74. Let me write that one down here, number 74. All right, so in number 74, we have the integral of x squared minus 1 divided by x squared plus 1 dx. So I'd like to, for this one, because this construct doesn't look like any of these formulas that we have up here, right? None of the inverse trig functions. So I need to work this a little bit. And in this case, let's do a long division. Okay, so we're going to do a long division of this one. So remember, for example, when we do 30 divided by 5. In the long division format, we write it 30 over 5. Quotient is 6. You multiply, subtract, you get 0. The answer is 6. Right? I'm going to do a similar thing in here. So in the long division, when we do long division here, so the numerator is x squared minus 1 divided by x squared plus 1, right? That's the divisor. We could divide first term by first term. First term in the what you call it, the dividend, what they call it. The numerator is dividend, denominator is divisor. First term in the dividend divided by first term in the divisor gives you 1. That's the first term in the quotient. You multiply by the quotient. You multiply divisor by the quotient, change sign and add, you get negative 2. So at this point, I can write this integral as that of 1. There's your quotient plus a remainder over a divisor. Right? So for example, let me show you that construct again. If I have 17 divided by 3 in the long division, 17 divided by 3, quotient is 5. You multiply, then change sign. That's why I changed sign here. Subtract. So the answer is going to be quotient plus remainder over a divisor. So the answer is 5 2/3. That's exactly what I did here with the integrand. I have the quotient is in here plus a remainder divided by a divisor. Okay, now we can work this one easily. The integral of 1, that's just x. Negative 2, integral of 1 over x squared plus 1 dx. And I know there is a constant of integration. Let me write it so it's not sloppy. It's because I integrated the first part. Call it C1. Now, the integral is exactly what's up here. 1 over x squared plus 1. There you go. 1 over x squared plus 1. So that's going to be arc tan of x. Okay, so the answer is negative 2 arc tan of x. And technically there will be a C2 as a consequence of this indefinite integral, but remember we combine the constants into what we call a global constant. That will be 2 arc tan of x plus c. There. All right. So there's number 74 for you. And then next we're going to look at number 78. Let me bring 78 down to work it. Alright, so here is exercise number 78. Although it looks complicated, but actually this integrand is a blessing in disguise. And the reason being the following. If I let u be secant inverse x, du, and we have du from previous work, one of our formulas for du is actually 1 over absolute value of x square root of x squared minus 1, which is precisely what's in the denominator of the integrand, dx. So that's good. We are actually given this part, the whole part of the integrand, this part, that, and there you go. You see that? That is all going to turn into a du for us, which is good. So suddenly, visually, things going to look much nicer. Check this out. Wow. That's going to be u cubed. Now, the integral of this, if I write it as u to negative 3 du, the integral is going to be u to negative 3 plus 1 over negative 2 plus a constant. Now, u was secant inverse, therefore the answer is going to be negative and 2 in the denominator. U to negative 2, that's secant inverse x to negative 2. There you go. Now be very careful, please. Do not multiply those. Negative 2 is an exponent, that's fine, but the negative that seems to be seeming like negative 1 on secant, that's just the inverse notation. In other words, this is maybe a better way to write it would be this. I just want to fit in the constant in there. So in other words, to make you believe that we can't do that, check this out. If I write this as arc secant x to negative 2, there you go. That's what that is. So you see that there is no negative to multiply by negative 2 in the exponent. So one thing I could do, because that's a valid negative exponent, I can move everything to the denominator. Not everything, but the arc secant. So the answer is going to be 1 over arc secant x squared, right? And then there is a 2 in front of that because of the 2 in the denominator. And since the books don't write them like this, I'm going to go follow what the book does. It's going to be written as 2 and then secant inverse x quantity squared plus a constant. And there you have it. So there's number 78. Okay, and that's my number 78. Let's take a look at another one. Let's do number 82, another seeming complicated expression, but again, I'm sure this is going to work out nicely for us. So let me copy number 82 down and then we work. Okay, let's take a look at exercise number 82. In exercise number 82, what I've done is I actually brought in the formula for integrals involving inverse trig functions here, and looking at what we have on the left and looking at the 3 integrals to the right, should be clear that we're looking at this one, the last one on our list. True? So let's see how this is going to work out. First, we're going to do some preliminary work that makes this look like the third integral. Now, one thing that's important here is the absolute value of u. Later on, I'm going to tell you the reason for the absolute value in the derivative of inverse secant, so it becomes clear why is there an absolute value there. But it's important that keep in mind what's in here, this factor, call it a factor. It's got to be positive, right? Because we know absolute value of u is positive. So this right in here, right now, we don't know if it's positive or negative. So we're going to make an adjustment in our answer in the end to accommodate for what I just mentioned. But let's proceed with this one. First, I'm going to make the integrand look as close as possible to the third integral here, this one. Okay. So let's begin by focusing inside in the radicand. It is very important again that we have a 1. Right now there is a 9. True? So first thing I focus on is on the constant. So the integral is going to be, here's dx. And let me in fact work the integrand separately. So if I have square root of x squared plus 1 squared minus 9, I'm going to factor a 9. Okay, we're going to factor the 9. And this is going to be factoring a 9. I'm going to have 9 factored out. So it's going to be x squared plus 1 over 9, right? And actually, sorry, it's just x plus 1 quantity squared. And I'm going to make that squared over 9. And then negative 1. Okay, and then I can rewrite now the radicand as x plus 1. And then square root of 9 times x plus 1 quantity squared over 9 minus 1. True? That's still what I started with. Now, next step, I'm going to rewrite the fraction inside the parentheses in the radicand. I'm going to write that as, let me actually do this. I'm going to make this as long as necessary. I'm going to write it as parentheses x plus 1 third quantity squared minus 1. Okay. And then I'm going to, sorry, I'm making all these adjustments. And then what I'm going to do is I'm going to take the square root of 9. It becomes 3, so I'm going to bring it all the way outside the radical. So that's 9 removed. And then I have dx over x plus 1. And of course, in the radicand, we have x plus 1 squared over x plus 1 over 3 quantity squared. X plus 1 over 3 quantity squared minus 1. That's what's in the radicand. And that's my dx, and here's x plus 1, and there's my integral. Okay. Now, it's easier to adjust everything to the radicand. So at this point, I'm going to make my u substitution. It's okay, I'm going to let u be x plus 1 over 3. And with that, that means 3u is equal to x plus 1. Therefore, 3 du equals dx. Good. So now I can also write the integrand as, instead of dx, I'm going to have, so remember there's 1/3 on the outside, right? Because I'm taking the square root of 9 right here, so it's going to be 1/3 on the outside. So this is going to be 1/3 of dx is 3 du, so there's 3 du. And then x plus 1 is 3u, and that's 3u square root of u squared minus 1. And then we can cross the 3's out. And now that looks almost like what's up here. Okay, now remember, absolute value here in the formula for the integral means this factor must be positive. Okay, so what I have right now is u. So in here, this form assumes u is positive in order to be able to use this formula. And the reason is that because if u is positive, is an absolute value of u if u is positive. Remember that? So we're going to assume that u is positive in this case. All right. Now, however, with our substitution, remember we're going to let u be x plus 1 over 3. x could be negative, right? Remember, we're looking at domain of secant inverse in this case. And the domain of secant inverse, let me write that, for secant inverse, our domain was from negative infinity to negative 1, union 1 to infinity. Okay, and so as you can see, x could be negative. Now if x is negative, that results into u becoming negative. So let me write that. Since x plus 1 over 3 could be less than 0, that would imply u could be less than 0, which contradicts our assumption here, right? So which is okay, we can proceed with this one. We just make an adjustment in the end. We put absolute value in their answer. Okay, so at this point I'm just going to write the integral is going to be 1/3. Okay, 1/3 of, and then I'm just going to write it as secant inverse, and I'm going to put absolute value of u here. For this reason, it's because in the beginning we weren't told that x is positive. X could be within the domain, and that means it could assume negative values. So to avoid a negative factor, we want this to be positive, u to be positive in the denominator, so we're going to put absolute value of u here plus a constant, and that's going to be 1/3 secant inverse of the absolute value of x plus 1 over 3. There you go. This was the problem right in here. Not the problem, but this was something we had to be wary of, because this expression could be less than 0, and if it's less than 0, then in the beginning, see that this becomes 0. Now this may be a good place to tell you why there is an absolute value in the derivative for secant inverse. Okay, and the reason is this. Let's say I want to find, so I'm just gonna put a note here. Let's say I want to find the derivative of secant inverse of x. Okay, and call that y. So I want to find y prime. Now by definition of inverse, secant y must be x, right? Okay, and if I take the derivative here, do implicit differentiation, derivative of secant y is secant tan y equal 1. Okay, and then from this, and of course times y prime equals 1, because we're doing implicit, right? The assumption is y is a function of x here. That's why we have y prime. Now if I solve for y prime here, y prime is going to be 1 over secant y tan y. Now secant y is x, true, so I'm just going to go 1 over x, and then tangent of y. Let's take a look at this one. We have the Pythagorean identity, tan squared y plus 1 equals secant squared y, right? That's a byproduct of Pythagorean identity, sine squared plus cosine squared equal 1. So from this we get tan squared y is equal to secant squared y minus 1. Okay, now remember secant squared y is right here. Secant squared y means x squared. Therefore tangent squared y is x squared minus 1, and tangent of y is the square root. We take it to be positive root of x squared minus 1, so that's square root of x squared minus 1. Now here's the justification for what becomes absolute value in here, and the reason is this, because if you look at again the range of secant, let me draw my circle again. Okay, so this is the range of secant inverse. We're looking at secant inverse of theta, let's say. All right, that's going to be from 0 to pi with the exception of pi over 2. Okay, now if theta is in Q1, theta belongs to the first quadrant, Q1, then that means secant and tangent are both positive, right? So the product, So if I look at secant y times tangent of y, that product is going to be positive, right? Now, in the second quadrant, let's take a look at that one. If theta is an angle in Q2, right, which is the range of our inverse, in there, well, again, secant is positive, right? Secant of y, because it's 1 over cosine. Secant is positive in second quadrant. And let's see, tangent in the third quadrant is going to be, actually secant is going to be negative, sorry. Secant is going to be negative in Q2, right? Because secant is 1 over cosine. In second quadrant, cosine is negative. So secant is negative. And also in the second quadrant, tangent is negative. Now look at the product again. Secant y times tan y, right? That product again will be positive. So it's positive regardless of whether the angle lies in Q1 or Q2. And to be consistent, let me put y in here, since everything I've written in terms of y. There you go. Now that makes more sense. This is secant inverse y, not the graph of it, but I'm looking at this is the range of secant inverse. So the point being this, everyone, therefore the derivative has to be positive. That's the point we were making. So in order to make sure that the product of secant y tan y is positive, the principal root of x squared minus 1, that's positive, we know that. So we make the adjustment by making x positive by forcing absolute value on it, so that we conform with this requirement. Okay, so it's for that reason where there is an absolute value in front of the denominator for the derivative of secant. Anyway, so that was a long explanation of why I needed absolute value on this one. Okay, it's because we're missing the absolute value in the original expression, which I didn't have. All right, so we are done with this exercise. Again, sorry, this took much longer than necessary, but the explanation was in order for that one. And let's take a look at, I believe it's the last one in this section we're going to take a look at, is number 86. Okay, so let me bring number 86 down and we'll continue. All right, here's number 86. Now I've again copied that brief table of integrals for inverse trig functions. Now again, judging the denominator, matching it against what's to the right. The first one and the last one involve square roots, and we don't have that, so these are out. So I'm going to focus on trying to make this look like the middle integral. All right, let's do that. Now to do that, remember the 9 is very important. That has to be a 1. So I'm going to begin by factoring a 9. Let me bring the 9 out, and here's how it's going to be. So this is going to become 1 plus ln of x divided by 3 quantities squared, right? So divided by 3 squared, because 3 squared is 9, so I went ahead and did 2 steps in one. I rewrote it with a denominator of 3 quantities squared, and you can kind of see now this is what the u is going to be, ln x divided by 3 in number 86. So I'm gonna let u be natural log of x divided by 3. That means 3u is ln of x, or 3 du equal 1 over x dx. All right, so we can rewrite the integral as that of 1/9. Now 1 over x dx And that's 3 du. That replaces this portion. And in the denominator, I'm going to have 1 plus u squared. And that's the form we wanted. The 3 in the numerator, the 9 in the denominator, make it 1/3 of 1 plus u squared du. That's precisely what the middle integral is. So that's going to be 1/3 tan inverse u plus a constant. And now I'm going to replace u with ln x over 3, natural log of x over 3. So that's arc tan of the natural log of x divided by 3 plus a constant. And that should do it. That was much easier than the one prior to that. And let's see, with that we are done with this lecture and with this section.